Good day and welcome to the Moscow Telecommunication Seminar. Our speaker today is Dimitrios Zorbas. Dr. Dimitrios Zorbas is an assistant professor at Nazarbayev University in Kazakhstan. He holds a PhD in computer science from the University of Piraeus in Greece. He has worked as postdoctoral researcher at Inria Lille, North Europe, at University of La Rochelle in France. He was also a researcher at Tyndall National Institute, University College Cork in Ireland after receiving a Marie Curie fellowship. He is an author of more than 50 peer-reviewed publications in the area of wireless communications and distributed computing. He has worked in several national projects as well as FP7 and Horizon 2020 projects. Today he will share his recent results about protocols for time-critical ad hoc applications. Dimitrios, the floor is yours.
Thank you for the introduction. All right, hello everybody. I'm going to present you some recent and not so recent work I have done in the past, but also here at Nazarbayev University in Kazakhstan. This is a general title, Protocols for Time-Critical Ad Hoc Applications. Just a few words about the university here. It's a quite new university, founded in 2010 with 8,000 students. It has very good facilities, a very nice research environment, and they recently got into 30%, top 30% research universities of the world. I arrived here 4 years ago, 3.5 to 4 years ago, and I founded the Internet of Things Lab. Currently, we have 4 master students and 15 undergraduate students that work as research assistants. We have equipment, more than 100 IoT devices. Our research is mostly hands-on. We have 3 main research projects right now. And the topics of the lab are actually, we develop protocols, custom protocols, or we improve already existing protocols. And we also do edge computing, machine learning, everything that can run on embedded systems and low-cost resource constrained devices. Okay, my today's talk is about time-critical and reliable IoT applications. So the applications we will deal in this talk are applications that are critical in terms of time, but not super critical. We're not talking about applications that require, for example, microsecond or even nanosecond of latency. Are a bit loose, let's say, applications that require a bit of more longer latency, let's say up to a couple of seconds or a bit more than that. I have some examples here, like file alarms, water leaks, train barriers, lighting systems. For example, when we raise a file alarm, it's not necessary the file alarm to be like with nanoseconds or microseconds of accuracy. Even if it is like 1 second, 2 seconds, is not a big deal. So we're talking about this kind of applications. What we have here is low, but not super low, but low and predicted latency. We need some bounds, okay? Not unbounded applications, and high reliability as well. Long range is most of the time required, and energy efficiency is most of the time also a requirement. Okay, the research question is how to employ long-range communications so that we support this kind of applications. Because with short-range applications, we can do it. Okay, there are existing technologies, wireless HART in the industry, TACH, time-slotted channel hopping, other technologies that can do that. But how can we do it with long-range technologies? For example, LoRa, ad hoc, mainly ad hoc radio technologies, ad hoc in the sense that we can use them in an ad hoc way without relying on external permanent infrastructure. So we mainly work the last years with LoRa. For those who don't know, LoRa comes from long range. This proprietary spread spectrum modulation, trades data rate with sensitivity, so distance. This is its main feature. So packets are transmitted with higher spreading factor, which is the #1 feature in LoRa, can achieve longer distances, but we lose in data rate. We can achieve very high ranges, up to 10 kilometers with typical LoRa antennas, typical equipment. And actually, this technology fits very well in our applications because it's super low cost and super low power consumption most of the time. It is resilient to Doppler effect, so we can even support satellite communication, for example. And it has super high penetration capabilities as well. We can use it, for example, in buildings. Okay, one of the first ideas that came up to the table was how to employ LoRa and time-slotted communication, how we can merge these kind of technologies, and in order to improve the reliability. Because if we use LoRa 1, it's based on an Aloha MAC, so we don't have the bounds that we want there, that I talked about at the beginning. So what is time-slotted communications? We have frames. The time is divided in frames and repeated frames, and each of the transmission is accommodated in one of these slots. And we have as well some guard times in between transmissions to accommodate, to tolerate desynchronization, so clock drift. Okay. Of course, this is not easy to do it. It is very easy to do it over like 2.4 gigahertz technology. We don't have duty cycle restrictions in most of the areas of the planet. It's super easy to do it. Here we have some design issues, as is written here, like radio duty cycle, as I mentioned, uneven slot length, because the payload, the transmission power depends on multiple things like the channel bandwidth, the spreading factor we use, some other LoRa-specific characteristics. Scheduling is important because it is super low data rate. Even if you compute the schedule, how to disseminate the schedule is an issue. How do you do acknowledgements? How you can send massive number of acknowledgements with a few only gateways, for example, because also the gateways have some limitations in terms of duty cycle, etc., etc. Synchronization is an issue. How to synchronize devices over a lossy channel. Propagation time. This holds for example, satellite communications, right? Propagation times plays a role here. Some security issues, battery lifetime, all these things are known, easily to solve with conventional 2.4 gigahertz technology, especially with high data rate technologies, but with LoRa, it's not so easy. Okay, I will go through this the next slides a bit quickly. So the first idea was to make a protocol, to develop a protocol to be able to run over LoRa 1. Okay, the main characteristics of that, approach was to use autonomous scheduling. What does it mean, autonomous scheduling? So each device autonomously decides about the slot, a unique slot, without relying on a third-party device. Okay? For example, a gateway network server to send out the schedule, to disseminate the schedule. And we came up with an approach here. I will not go into much detail to explain the approach. We can read the paper here. one of the first approaches. It was published in a workshop. What we actually do, I have an example here. We take into account the already registered DVUIs, like MAC addresses of LoRa transceivers. Let's say we have these 5 DVUIs here. We convert them to unique integers. Let's say these are the unique integers. And then you need to compute a k, a minimum k here, so that each of the numbers here, modulo k, correspond to a unique slot. For example, in this particular example, k is 9, equal 9 is the best case. As you can see, these 5 nodes can be accommodated to 9 slots. What is the advantage of the solution? We send only number 9 to the devices, and then the devices do this simple calculation here. For example, this device 26, 30, 71, 585 will do DVUI modulo 9 and will find its unique slot, which will be like number 2 here, or number 1 if we start from 0. The issue with this solution is that it leaves empty spaces, as you can see, empty slots, and we don't want that. Actually, what I just described is a perfect hash function. Okay, we make a perfect hash function. We have the keys, which are the DVUIs. We invent a hash function. We find a hash function, and we calculate the hashes, which are the slots. In order to avoid this problem with the empty slots, we need a minimum perfect hash function, which is not so easy to do it. Some results here, simulation results, but also experiments. The problem with this approach is that with very high number of end devices, as you can see, the frame size gets super high. For example, the frame, even with 300 devices, it gets, with 100 devices, it gets like 15, no, it's like, is a logarithmic here, it's like 30 to 50 seconds because of the empty slots that we have there. But of course, it works in terms of PDR. If you have like low number of end devices, you get the PDR because we have unique slots. You get the PDR very close to 1. Only the path loss is the problem. Compared to default LoRa 1, default LoRa means default LoRa 1 here, you have much higher PDR. The problem is when we start having very large number of end devices, what happens there? So to fix that issue, we came up with another solution. So to solve the problem with empty slots, still collision-free, autonomous as well. But this time, we changed the way we generate the dev address, the device address when a device registers into a LoRa 1 network. Okay, I will not go into detail again. There is a mechanism here how we can do that, a simple while loop actually. We regenerate the dev address until this modulo operation, S is just a fixed number constant that all devices know, until this random 32-bit dev address gives the desired slot. Okay? Let's say we have a device, for example, that we need to accommodate it in slot 5. We keep generating dev addresses until this simple calculation here, modulo operation gives slot equal 5. This is super fast, as you can see here. Even with 1,000 devices, the execution time is 6 milliseconds. We came up with a frame structure as well, repeated frames. We supported acknowledgement this time as well, even though the acknowledgement mechanism is not compatible with LoRa 1, but it can be used separately on an overlay on that application layer. We implemented that using ESP32 devices, 24 devices. We checked that on, actually, we did that when I was in Ireland as a Marie Curie fellow in four-floor building using a single gateway. The gateway was somewhere in the middle, in the second floor. And we got super good results, actually, super high PDR, even with devices that were much very far away from the gateway, could get PDR of more than 99.8%. Okay. Now, recently, we extended that solution to support actuators. So this is a typical LoRaWAN architecture. As you probably know, we have the end devices. The end devices communicate with the back end, which is one or more servers, network server, the joint server, application server, etc., etc. It can be also like one machine, all in one. This is a typical LoRaWAN architecture. This typical LoRaWAN architecture does not support actuating. Okay, you can send uplinks. You can send downlinks like LoRaWAN commands and acknowledgement, but you cannot send like specific commands. Do something. You cannot do that over LoRaWAN. Unless you synchronize the network, you assume that you have LoRaWAN class B devices, for those who are familiar, and then have an overlay over LoRaWAN class B and send specific commands to those devices. So the problem is how to enable device-to-device communications here. We don't want the communication between an end device and an actuator to be through a network server, but to be direct. So when you have, for example, an end device, a sensor detects a fire, okay? We don't want this end device to go through the typical LoRaWAN architecture, through the network server, and then the network server, through an overlay, let the actuators do the job, like activate, for example, an extinguisher or fire alarms, all this stuff, okay? We want the end device to directly communicate with the actuators. Okay, we want this to be autonomous, to be as efficient as possible, as reliable as possible. We base this idea on the TS LoRa idea that I showed you previously. We extend that using, actually the typical sensors follow the LoRaWAN architecture, but we also have actuators here that are still part of the same network, but they follow a time-slotted form of the network. And there's some math here about how we can do that some XOR operations to calculate the keys, the dev addresses, what dev addresses we give to those actuators so that can directly communicate with an instigator. Instigator is the sensor, the one that generates the alarm, for example. You can check this paper that was published a couple of years ago in ICC, how this can be done in detail. Again, here we have some, we run some experiments and simulations as well. What we can see, even with 3 channels, we have a very high packet success rate. It's over, even with 1,000 devices, for example, which is insane for a LoRaWAN network, to support 100 devices with a single gateway. We have a success rate of 75, let's say, %. And of course, we have like a fixed, very fixed energy consumption. Okay. There are some other papers as well, some other work that we have done related to that, variations of the same stuff. But let's talk about a research project that we have here that is more or less what I described now in the last slides, but applied on a real scenario. So what is the problem that we have? in that project. This is the map of Kazakhstan, is the railway map actually. As you know, the territory of Kazakhstan is huge, like Russian territory is the same, huge territory. Kazakhstan is even sparser populated than Russia. So it's not easy to deploy a permanent infrastructure, especially in rural areas, all right? Kazakh railways rely on a tetra permanent infrastructure. I don't know if you're familiar with tetra. It's actually old protocol, let's say from 90s, early 2000s, that is used in telecommunications, especially in railway systems. It is long range, it is efficient, but it requires permanent infrastructure. We cannot do anything without towers, all these things. So the problem is that because of the lack of a permanent infrastructure, let's say we are here somewhere in the middle of between cities and we want to fix some rails that were damaged. The workers must know that a train is approaching when they are fixing the rails. This is the problem. We need a notification, an alarm mechanism to let them know that something is coming. Okay, so that we have some workers working on the rails. In general, the safety measures in Kazakhstan are not the best. I don't know how it is in Russia. Usually what we are talking here about freight trains, okay, not passenger trains. So freight trains are slow in order to save fuel, to save diesel. They go like 50, 60 kilometers per hour, maximum 80, let's say, 80 kilometers per hour maximum in the best case scenario. So this is the concept. And what we are developing here is a system consisting of several components. We have some LoRa devices that are deployed on the trains, on each of the train. We have a portable station device. We call it station, but it has nothing to do with a proper train station, okay? It's just a device. And the train with the device, this device communicate with each other, exchange coordinates, and let each other know that they exist in the neighborhood and raise an alarm, okay? They raise an alarm here. Here we have two types of communications. We have the long-range communication between a train and the station, or more stations. And then once the station receives a signal from the train, propagates that signal through a mid-range protocol called ESP-NOW. I will talk in a while about that to the workers. Or it forwards this train signal to a tetra station. Okay, for those who are not familiar, ESP-NOW is a full-stack communication protocol developed by Espressif. Is actually the company, the manufacturer that develops the ESP32 devices, all the ecosystem of ESP. It employs the 802.11 technology, super cheap. And we employ that radio technology because it is compatible with the devices we have in the lab. It is connectionless, doesn't require like, doesn't have overhead like Wi-Fi. There is also a proprietary long-range mode, which achieves a bit of longer range compared to the simple 802.11. So this is the general overview. So we have beacons that are transmitted by this station device, LoRa beacons, every while, 3 to 5 seconds. And once this beacon is received by a train, we send the response. We also have some tablets here, some other equipment. This is part of the same project, but not related to what I'm going to present now. So we send the response with our coordinates. So in this way, we know more or less the speed of the train and where the train is located right now. And so we can calculate in how much time it will approach the repair site. And we inform the workers here accordingly using a custom protocol that we have developed over ESP now. Some details here about the station layer, how often it sends messages, how big are these packets. We also have a machine learning model here to estimate the RSS, the received signal strength of the packet, of the train packet when the coordinates of the train are not received, because the GPS sometimes malfunctions and we don't get GPS coordinates. And so we can estimate using some experiments. We run some experiments, several experiments, actually with thousands of packets, different positions, and we trained the machine learning model for 3 different terrain types. At the train layer, in order to avoid collisions, if a beacon is received actually when a beacon is received by multiple trains at the same time, let's say we have a train that comes, we are here in the middle, and a train comes from this rail, and another train comes from this rail. Both of these trains will receive at the same time the beacon. If they respond at the same time, then we're going to have most likely a collision at the station. Perhaps one or none of the signals will be received. In order to avoid such situation, we schedule the transmissions of the train, so the responses here, based on the direction of the train, of each of the trains. For example, if the train comes from that direction, it will choose slot 1. If it comes from this direction, it will choose slot 3. We tested that, and it was actually working fine. We support up to 4 trains, even though this scenario, at least in Kazakhstan, is extremely rare, or if not impossible. We usually have just a double rail and nothing more. We don't have like junctions. We're talking about rural areas, not inside cities. Inside the cities, yes, it is possible to have it, but inside the cities, we're not going to use such system. There are other systems that can be used that are more reliable. They rely on wires. We don't have such issues there. We also calculate some probabilities here based on the probability of if we receive the probability of receiving the beacon of the station, and the probability of receiving the response of the train at the station. So there is some math behind in order to give some bounds and have some specific time constraints in our approach. Now, this was about the station train communication, the LoRa communication. We also developed, we actually extended the ESP Now protocol to make it multi-hop, but also make it more reliable by transmitting multiple copies of the same packet. So we get the response of the train, we propagate it to the workers. The workers have a wearable device on their wrist, and this wearable device has gives some feedback with vibration, with some light, and lets the workers know that the train is approaching. It also it has some beep and shows the duration, the arrival time of the train. So in order to make this protocol more reliable, we send multiple copies of the same packet 3 times, up to 3 times, and up to n hops. So we actually increase the probability of transmitting, of receiving, delivering a packet to a device that is not so reliable. Maybe the device is far away, or it may not receive the packet using the first hop, but using the multi-hop flooding mechanism. This is a flooding mechanism. It will receive it using another device that is nearby, or a couple of devices, or more than 2 devices. We have a proper communication protocol here, time-slotted protocol. We have different versions of the protocol. If the device goes to sleep, if it doesn't go to sleep, we usually keep the devices on in order to minimize the latency there. But we have a trade-off here between latency and energy efficiency. Because if you leave the devices on, you minimize the latency, but you spend more energy. So we run some experiments here to see what is going on indoors, but also outdoors. With line of sight, the ESP now has very long range. It sometimes reaches 200-300 meters, the long range mode of ESP now. But sometimes it's not so reliable because it also depends on the antenna you use. The wearable device has an embedded antenna, very low dBi. It is easy to miss packets. What is interesting to see here, sorry, these are the experiments for the LoRa communication first. We measure the repeated losses, how many repeated losses we have with a distance, for example, of 500 meters, 1,000 meters, and 1,550 meters. So based on these experiments, we can set bounds and actually decide about how often to retransmit a beacon, all right? By increasing the number of beacons per time unit, you increase the probability of receiving certain amount of beacons per time unit at a train, from a train. So based on this probability and the repeated losses you have, you can adapt your protocol and your time bounds accordingly. And this is the response time, depending on what slot we use. So the maximum response time here, as you can see, even with 5 slots, is 2.26 seconds. So from the time a train is detected, we need 2.26 seconds to let the workers know. And this is the Sync ESP Now result. As you can see, we can achieve with time to leave equal to, so flooding with 2 hops, 99.95% of PDR. This is some power characterization we did for the wearable, how long it will survive, and what is the energy consumption for different modes of the protocol. If it is always on, or if it uses like time slotted with sleep times in between. And as you can see, even with N is the number of, is the time to leave, actually 2 hops and 3 retransmissions. The energy is super low, it's 31.8 milliwatts, the average power consumption, which is super low. This means that that with a simple 1500 milliampere hours battery, we can achieve a lifetime of several days. 10 hours is if it is always on. So is this 5333. Okay, recently we started using machine learning, how to make communication more efficient, to adapt to different scenarios. For example, a typical problem we noticed is the synchronization efficiency when we talked about synchronized protocols, time-slotted protocols. As you know, the devices, especially these chip devices, drift over time. Okay, the real-time clock drifts over time, and drifts over time actually considerably and differently to in each of the devices. The drift time is affected by multiple factors, from the environmental temperature, from the voltage of the battery, the aging of the crystal oscillator, many things. So we started using some reinforcement learning approach here in order to optimize the sleep time on the end device without knowing what are the characteristics of the end device. And these are some preliminary results that we have actually submitted to a conference recently. This is the reinforcement learning approach with a solid line, and the non-reinforcement learning with a non-solid line. As you can see, you can assume this delta is the how long we stay on until we receive the beacon, a beacon, for example. As you can see, so it starts calibrating here, and after 100 iterations, is more or less calibrated. So it let's say converges to a value of this particular device to a value of 8 to 10 milliseconds. A problem that we also noticed is the energy consumption, especially when we use synchronization. We have an extra cost there because the devices have to wake up to receive the synchronization beacons. All right. So we have a bit higher energy consumption in the end. We started using solar panels, small solar panels, and the approach here actually correlates the ambient light. We have some sensors that measure the ambient light, and we also have a power sensor, a current sensor. It measures the current, and we correlate the current with the ambient light that we get from the sensor. Why we do that? Because we need to know, to estimate every time we wake up, how much energy is stored in the battery, how much energy has been generated by the solar panel and stored in the battery. We ran some experiments here for several months, and we trained the machine learning model with different machine learning models, random forest, neural networks, all these approaches, and we compare them to the truth here. This is the ground truth. So this is the estimated energy that was generated by the solar panel, and the ground truth. Okay, as you can, this is for different periods of time for a specific day. Approximately 3 weeks ago, 3-4 weeks ago. As you can see, actually, some of the algorithms are quite close to the real value, as you can see. So this really works. I have some extra slides if you want to see later. And we can actually predict how much energy was generated by the solar panel and schedule the transmissions and the wake-up times accordingly. Okay, I will stop here. If you have any questions, I will be happy to answer them.
Thank you, Dimitrios, for your interesting presentation. We have several questions in the chat window, and the first one from my side. When you talk about your first results on TS LoRa, you do not cover the question of latency, because it seems to be clear that the time-slotted structure increases latency. And what's the order of latency in the network?
Well, we have some bounds there that are actually 1 frame size. Now, it's up to the application, depends on the application requirement to set a maximum length for the frame. Usually the frame is, let's say, 5 seconds. So we have a maximum latency there of 5 seconds. Of course, as long as you increase the number of end devices, I think with spreading factor 7, for example, and 16 bytes, we can support up to 100 something end devices without increasing that 5-6 seconds of latency of frame size. So this is the maximum latency that we have. Of course, in order to support more gateways, more end devices, or decrease the latency, we need to add more gateways that can run in parallel over a different frequency, for example.
Okay, thank you. I guess that's 5 seconds is enough for applications you consider. So,
yes. For this kind of application, I think it is fine. Yes. Now, if you want something that requires 1 second of latency maximum, you must switch to another radio technology, of course.
Okay, thank you. The next question from Dmitry Bankov.
Hello again. Thank you for your talk. So I have a question. Many time-slotted schemes that you described, they have a problem of scalability, and many problems like this could be resolved if devices listened to the channel before transmissions. So if they applied some kind of listen before talk schemes. And as far as I know, there is some research about using listen before talk schemes in LoRa. Do off-the-shelf devices support such transmission modes? Can you use them to solve?
Well, yes, we have tried CSMA as well. The problem with the CSMA, it doesn't give these bounds that we want. And also the reliability is not so high as with time-slotted communication. Here we can achieve a reliability of 99.8%, as you saw. CSMA is still okay, but not at that stage. Let's say when I tried that was around 90-something%, but the devices were super close to each other. If the devices are not so close to each other, then the efficiency, because of the hidden terminal problem and all this stuff, is much lower.
Okay, thank you.
There is the CAD mechanism in LoRa, CAD, that you can use, which is very energy efficient, but it relies on the specific spreading factor. If you have multiple spreading factors over the same channel, then CAD doesn't work well.
Okay, thank you. The next question again from my side. When you speak about LoRa for actuators and show the graphs of PDR, and they are close to 1, but not exactly. So you have some losses.
Let me share my screen as well.
Okay.
So you're talking about this case, right?
Actuators. Yes, this one. Yes.
Yeah.
So my question is, as far as I understand, in synchronized scheme, you don't have any collisions. So if you don't have any collisions, why do you have?
Because the channel is shared. We still use the same channels for the Aloha-based devices and the time-slotted devices. That's why. If we use a separate channel, then we're not going to have any collisions. It would be like linear, completely linear here, straight, fixed. Okay, this is the reason.
Okay, I got it. So you have some other devices which you don't use your protocol. That's clear. Thank you. And the next question from Anton Karamyshev.
Okay, hello. May I ask several questions related to train scenario? First of all, as far as I understand, LoRa 1, or let's say just LoRa transceiver, is then placed on the top of the moving train, and we assume at least 60 kilometers per hour speed, yeah? So my question is, have you tried to evaluate it in the real scenario with a moving train? Because I assume there is a something like a Doppler shift or a Doppler effect, and then the frame transmitted from the train is likely to be distorted.
Yes. We tested it with cars. Actually, this is an ongoing project, and we will soon start proper field experiments with the devices that we have developed. But we tested it with cars. With line of sight, the maximum range, because we use also spreading factor 10, we don't use the maximum spreading factor. With spreading factor 10, the maximum range was 5.6 kilometers, the maximum reliable range. Reliable range means that we reach a point that we don't really miss many packets. So 5.6 is with line of sight. Now, if we start having obstacles, trees, many other cars, it depends a lot on the altitude as well. How high is the antenna? Then we start.
I mean, if the okay,
about the Doppler effect. About the Doppler effect,
yeah,
it's not really an issue in LoRa. It's very resilient to Doppler effect. There are also some articles in the literature that they show that even with satellites, for example, LEO satellites, that they travel with hundreds of thousands of kilometers per hour, it's not an issue. You can still receive a LoRa packet. So Doppler
even
effect
at 16 kilometers per hour, right?
Yes.
Okay, thanks. And maybe my second question related to that, you have shown the PDR around 99%, but I assume in that such a scenario with humans, we probably want more. Can you a bit elaborate on that?
You're talking about this result here?
Yeah, probably this.
Yeah, actually, these are results with the wearable on humans. So it's not with devices like proper antennas, big antennas. It's with actual wearables. So the results here are real. And
I mean, may I clarify a bit? If we have a PDR, or let me switch to the PLR, which is a packet and loss ratio around 1%, this 1% may cause a disaster with humans.
Okay, understood what you mean. Yes, actually, usually this is not the only approach that we have. I have it here. We also have this device. This train signal is propagated to that device as well, which is a tetra device carried by a worker that is responsible for the shift, the supervisor, let's say. So this is used as a second security mechanism. And we have a third security mechanism, which is something that I didn't mention, is another device that is placed 1 kilometer away from the repair site. It uses machine learning to detect trains from vibrations. That device communicates with the station device as well, and is used, as I said, as a third security mechanism for that system.
Okay, what new kind of reliability level can you provide with such a scheme?
This is the purpose of the test field experiments right now.
That's okay, I see.
We are in the process of taking permission now, and to deploy on real trains.
Oh yeah,
this is the last stage of the project.
I get it. Thanks. Really interesting.
Thank you. The next question from Ekaterina Stepanova. Which guard intervals did you use in slotted systems, and what is the typical clock drift in LoRa devices?
Okay. Actually depends on the microcontroller you use. ESP32 devices drift a lot because of the real-time operating system that runs in the background. If you use like STM32 devices, the clock drift is some microseconds. Here it is some milliseconds. It's 1,000 times larger than STM32 devices. We use the ESP32 device in this stage because they are super cheap. We want to have something super cheap, and we don't care if it is like some milliseconds of latency more than other devices. So typical clock drift, let's say, is a few microseconds per minute. Okay, this is the minimum you can achieve, but it may be much more than that. It may be milliseconds per minute. For example, in those in TS LoRa, for example, we use 10, 15 milliseconds just to be sure to accommodate the maximum clock drift we could have among devices. It depends a lot of the hardware. The clock drift depends a lot of the hardware. If the crystal oscillator is a very good quality, then you can achieve even 1 microsecond of clock drift, even less than that.
Thank you. The next question from Dmitry Bankov.
So one more question. You showed the picture where there was an intersection of railways, like four trains, and you said that you assigned different time slots to trains moving to different directions.
Mm-hmm.
And why not separate them by channels? Like you have at least 3 channels, frequency channels.
Yes, good question. The problem with channels here, the station device can listen only to 1 channel at a time because it's a simple LoRa device. It's not like a concentrator. If we use a concentrator, which has a bit higher cost, then it is possible to do it. You can use a channel because the concentrator can listen, LoRa concentrator can listen to up to 8 channels at the same time. Okay, in that scenario, yes, you can play, instead of playing with slots, you can play with channels. But the number one requirement in this project is the cost. Okay, they wanted something to be super cheap, not exceed like $100 per set. Set, I mean, station train.
Okay, thank you.
So I guess that's all for today. Let me thank Dimitrios for a very interesting talk, and let me also thank all the participants for fruitful discussion. See you at the next seminars. Goodbye.
Thank you for the invitation. Have a good evening and see you soon, I hope.
See you. Goodbye.
Bye-bye.